The ethical routing example provides concrete targets. Fairness is defined as at most a 20% difference in service time outcomes between neighborhoods. Environmental performance targets a 25% reduction in carbon dioxide emissions. Driver welfare limits shifts to 8 hours with mandatory breaks. Vulnerability priority reserves 15% of capacity for elderly and disabled customers. The reported auditing outcome includes a 94% equity score and a bias index of 0.02. Tier 9 introduces quantum optimization concepts. The idea is to encode routing decisions into binary variables and then optimize using quantum-inspired or quantum-native methods. Quantum approximate optimization alternates two operators. One represents the routing objective and constraints, and the other encourages exploration across solutions. The goal is to reach near-optimal solutions faster for very large instances. This figure shows a quantum circuit perspective of the quantum approximate optimization approach. The circuit applies repeated layers that mix exploration with problem-specific structure. While practical quantum routing is still emerging, this framing clarifies how a complex routing objective can be represented and optimized in a fundamentally different computational model. This slide summarizes the state evolution idea in words. The algorithm applies alternating operations controlled by parameters that are tuned by a classical optimizer. Operationally, you can interpret this as a structured search procedure. You adjust parameters to increase the chance of measuring high-quality route assignments, analogous to tuning a meta-heuristic but within a quantum circuit framework. The quantum example considers a metropolitan network with 75 customers, 8 vehicles, and 127 time window constraints. Using a 127-qubit processor and 6 optimization layers, the reported solution time is 15.7 seconds, including parameter tuning. A classical benchmark is 2.3 hours for similar quality. The reported result is 99.7% of known optimal and a 526 times speedup. Tier 10 changes the problem by shaping demand rather than only solving routes. If customers can be nudged to accept different delivery times or consolidate deliveries, VRPTW becomes easier. Mechanisms include time-based delivery fees, discounts for off-peak windows, and neighborhood coordination rewards. The goal is to smooth peaks and increase route density, which improves vehicle utilization and reduces travel time. This ecosystem diagram shows how pricing, nudges, and gamification influence customer choices, which then changes the feasible routing landscape. For VRPTW, the most practical benefit is shifting deliveries away from congested windows and enabling better batching. That reduces both total distance and the risk of missing tight receiving windows. In the urban grocery delivery example, dynamic pricing shifts 34% of demand away from the 5 to 7 p.m. peak window. Consolidation incentives increase multi-household deliveries by 67%. Behavioral nudging reduces delivery location changes by 28%. The reported routing results include 41% improvement in vehicle utilization and 29% reduction in total travel time, along with a 35% reduction in per-delivery carbon footprint. These practice questions are designed to make you implement and explain each tier. For Tier 1, you must write the full mixed integer formulation for a 4-customer instance and solve it using Euclidean travel times. For Tiers 2 and 3, you implement and trace heuristic logic and then design a penalty-based meta-heuristic. For Tiers 4 through 10, you design learning, simulation, autonomy, ethics, quantum encoding, and demand-shaping components, always grounding your choices in operational realities. To close, remember the core lesson of VRPTW. Operational feasibility comes from respecting time windows, service times, and capacity at the same time. Exact models provide a rigorous baseline, but scalable heuristics and learning-based approaches make the problem solvable in real dynamic cities. The advanced tiers emphasize that routing performance is shaped by data, human judgment, ethics, and even by influencing demand patterns.